In this unit, I'll be doing a few examples of vector addition using components. I would really recommend that you have a calculator with you for this lesson because there is a couple places where I'd say, now you try. So if you have a calculator that especially it needs to be able to do tan functions, so to be able to do some trig in there would be nice. Okay, let's take a look at this first one. It says, when vectors are all either vertical or horizontal, it is easy to add them. So let's consider this one here. And in fact, this would be very much like, I'm going to try to get up my arrows here again. If I was to say adding these together, the 7 and the 5, to make one that looks like this, and then if I add another arrow that kind of looks like this. Oh, I didn't do too bad of a job, but kind of something like that. I wonder if I can move these arrows around. So, oh, this is kind of weird. Okay, so that diagram, it'd be very similar to having just a diagram that looks sort of like that, okay? So you could say, I want to replace this diagram with that diagram. So if that makes sense to you. So what we could do is we could add all the x's together and add all the y's together, right? So the x's together would be 7 plus 5, and this one would be 5. And so if we can get all the x's added together and all the y's added together, at that point then it's a fairly straightforward process to say what's the resultant, right? And what is the angle of the resultant, right? So here, let's even finish it off. The resultant is going to be equal to, oh, I don't want to have that color, is going to be equal to the square root of 12 squared plus 5 squared. In case you didn't notice, 7 plus 5 is 12. So that answer is 13 right on the dot. It's one of those cool Pythagorean triples, right? You got your 3, 4, 5s, but don't forget your 5, 12, 13. It's a really handy triple. So the angle in this case, the theta here, it's going to be the inverse tan of 5 over 12 because it's the opposite over the adjacent, so 5 over 12, which is around 22.6 degrees. So the answer for this one would be 13, and let's not forget our units, meters, at, now since this is in the first quadrant, I'll draw my XY grid, since it's in the first quadrant, my theta is, I don't have to add or subtract 180 or 360 or anything like that. We're good to go, 200.6 degrees. So there is our answer. Very nice. Okay, so there we are if we had them all either vertical or horizontal. Well, if they're not all vertical or horizontal, here's an example of one that's at an angle. What we can do is we can say we're going to break it into components that are vertical and horizontal, or vertical or horizontal. Instead of breaking, we use the word resolving. Okay, so what we're going to do is we're going to start off with this vector here. I'll just draw it again. Start off with this vector, and I think we're calling it T because it is a tension force of a chain or a rope. And we're going to say I'm going to replace that with a horizontal component, a Tx, and a Ty. Okay, and so if I was to do this diagram, of course I could not draw a dog that nice, but let's say here was my original diagram with a T. I could redraw it afterwards and replace it with Tx and Ty. So instead of having this one, I have these two. These two added up, Tx and Ty added together, is the same thing as my original T vector. So I start off with this vector and I resolve it into components, and then I replace this one with these two. And they're so much easier to add because they're vertical and horizontal. Okay, so let's do this one. It's 60 newtons at 40 degrees. So my Tx would be equal to, well, let's think here. Here's 40 degrees. This side is 60. X is my adjacent side, right? Okay, so I'll just erase this for a second because I'm going to think, okay, the adjacent side and the hypotenuse, that means I'm going to be using cos. So, toa. Cos is the adjacent over the hypotenuse. Adjacent over the hypotenuse. So I'll say the cos of 40 degrees is equal to the adjacent side, tx, over the hypotenuse, which is 60. Now, if I want to get tx by itself, I would multiply both sides by 60. So I would say that, maybe we'll just draw an arrow here showing that I'm going to rearrange things. 60 times the cos of 40 degrees is equal to tx. So in other words, tx is, when I do 60 times 40 degrees of cos, oh, you know what, I don't know offhand. So that's some number, okay? And then ty, looking at it very similarly, ty is going to be the opposite over the hypotenuse, so it's going to be sine. So let's look at sine here for a second. The sine of 40 degrees will be the opposite, ty, over 60. So ty will be, when I multiply both sides by 60, 60 times the sine of 40 degrees, which I'm actually just going to leave blank. I'm not too concerned what the actual value is. If you'll notice, and I think you may have seen this from grade 11 as well, there is a pattern here, okay? So if A is the name of the vector, in this example it was t, right? So let's just say if we had, I'll draw it over here, tx was equal to 60 times the cos of theta, and ty was 60 times the sine of theta, okay? Where 60 was the magnitude of the original vector. So this is a little fancy drawing here, this absolute value of a thing. That's the magnitude of the vector. So if you have a vector and its original magnitude is some amount, so if I have, here's my vector a, right? It had the length of this line, that's what a is. I'm going to multiply it by the cos of the angle to figure out the x component. So it's kind of, if you can associate cos with x, then you're good to go. So the x component will be a times the cos of theta, and the y component will be whatever the magnitude of the vector was multiplied by the sine of the angle. So this is a kind of a good one to remember. So let's try it. Let's do a couple here. Find the x and the y components of 40 newtons at 30 degrees counterclockwise from east. So if I went 30 degrees, maybe it looks something like that. So this side is 40. This angle inside there is, 30 degrees. And so this would be my x component, and that would be my y component. I'm going to call this a force vector. So I'm going to say the original vector I'm going to call f. So this would be fx, and this one will be, if I can fit it in here, then fy. Kind of messy, but I think it'll work. Fx is going to be equal to the value of f, so the magnitude of f, multiplied by the cos of the angle. The magnitude of f is 40 multiplied by the cos of 30 degrees. 40 times the cos of 30 degrees is 34.6 newtons. I'll check my units out. It's got to be a habit to think about your units at the very end. The Fy, very similarly now, looking over, just remembering that the y component is whatever the magnitude is multiplied by the sine. So it's going to be the absolute value of f multiplied by the sine of theta. So that will be equal to 40 times the sine of 30 degrees. For those pre-cal students with an excellent memory, you'll say, hey, sine of 30 degrees is a half. 40 times a half turns out to be 20 newtons. Okay, so you could say, but Mr. Speiser, what about the direction? Well, positive 20 in the y direction, that's kind of got your direction. This y is already saying that that's in the y direction positive. This is in the x direction positive. Okay, let's try this the second one here. 15 meters per second at 100 degrees counterclockwise. So here, I'll draw the diagram up here so I have a bit more room. 100 degrees is going to be, well, here's 90. It's a little bit past 90, so it's going to go that direction. Okay, so this is 100 degrees in there, not 1,000, it's 100 degrees, and this is 15 meters per second, the length of that arrow. So this is pretty neat that we can just follow that same pattern. I called this one f because it looks like a force vector. This looks like a velocity vector, so I'm going to call this v. Okay, so I'll say vx is going to be equal to, look at the same idea. The value of this is 15 times the cos of 100 degrees. Now, I would recommend you to get your calculator out. Multiply 15 times the cos of 100 degrees. Make sure you're in degrees. And here's what's neat. What happens when you come out, it ends up being a negative 2.6. And negative 2.6, I'm going to add the meters per second in there. So why is it negative? Well, look at the diagram. You know, x goes positive this direction, negative in that direction. So it does go a little bit negative, right? So it would go about that much negative, right? So it's negative 2.6. Vy is going to be equal to 15 times the sine of 100 degrees. And putting that into your calculator, we should get 14.8 meters per second. Okay, this last one did a little bit of a trickiness thing here. We have to think about this 20 degrees south of west and convert that into counterclockwise. So let's think about this, south of west. So look west and then go 20 degrees south of it. So it's like this, okay? So if this part's 20 degrees, what is it counterclockwise? That would be the same thing as 20 degrees plus 180 degrees, because of which quadrant it's in. So that would be 200 degrees. 200 degrees. So 10 meters. We'll call that a displacement vector. We'll call it delta d. So delta dx. How far does it go in the x direction? Well, it goes 10 times the cos of 200 degrees. How far does it go in the y direction? Well, it goes 10 times the sine of 200 degrees. So our answers work out to, once you get your calculator out, negative 9.4 meters and negative 3.4 meters. Pretty cool stuff. Okay. Okay, let's go on to the next page and let's add the following using components. Now, there would be a pretty easy way to do this by drawing an arrow across there. I'm just going to show you a method. Right now it might seem like it's a little bit of a long method, but you're going to see over the course of the next couple examples that it really works well. So first of all, I'll just name these vectors. So I'll call this one A, this one will be B, try that better, that one is B, and then this one, which is at an angle, this is the tough one, isn't it? That one's at C. And I'll say, okay, I want to add together these vectors. I'm going to add A, I'm going to add a B, and C. And so what is A? A is 5 meters north. B is 9 meters. Which direction is that? East. Always have to think about that east and west. And now C is the bit of the tougher one. This one is 14 meters. And now we have to think about what that direction is. Okay, so looking at where the vector starts, I'll draw that east-west line there, and I think, okay, so the counterclockwise from east is going to be that direction there. So C looks like it will be a full loop of 360 degrees minus that 45. So it seems to me that that would be 315 degrees, right? 315 degrees. So now I'll say that vector C is 14 meters at 315 degrees. Now when I think about, okay, the x and the y components of each one, the x and the y. Alright, so ax is going to be equal to, well, how much does this one go in the x direction? Really, none at all. It goes straight north, right? How much does it go in the y direction? It goes 5. Now, b is straight east. Straight east is in the positive x direction. So I'm going to get a 9 here and 0 in the y direction. Okay, so far it's just thinking about whether or not north is x or y, and thinking about whether east is x or y. Now the last one, this is where we're going to apply what we just learned about this, doing the magnitude multiplied by cos for the x and magnitude multiplied by sine for the y. So I'm going to say the x direction is going to be equal to 14 multiplied by the cos of 315 degrees, and in the y direction, I'll just zoom in, it's going to be 14 multiplied by the sine of 315 degrees. Now here's something that's neat. You don't even have to like take the time to type that in and then write down the number. You can do this all at once. So the sum of all the x directions, that will be the x component of the resultant. Okay, so 0 plus 9 plus 14 times the cos of 315 degrees turns out to be 18.9. And the sum of all the y directions will be the resultant, the y component of the resultant, and that will be negative 4.9. Let's see if we can make sense of that. Okay, so looking back at our original vector here, I'll just clean this up a little bit. Looking back at this one, the resultant is going to start here and it's going to end there. So my resultant here, let me see if I can draw one of those crazy lines again. See if it works at all. So my resultant is going to look something, oh, I can't quite, there we go. My resultant is going to be over there. Thinking about the direction. Okay, so the x amount will be 18.9. So here is the x amount. That is 18.9. It's 9, there's the 9 part, plus whatever the x component of that was, right? The y component of the resultant is this one. So this is Rx, and this one is Ry. Okay, I'll just redraw that down here because it kind of makes good sense. Here is Rx, and here is Ry. And we figured Rx was 18.9, and Ry was downwards, and my arrow is downwards, so I don't have to write the negative again, is 4.9. Now what I need to do is figure out, well, what is the resultant, right? What is this resultant side? What's the r, and what's the theta? Okay, so the steps here are to say that r is going to be equal to, just like Pythagoras, the square root of Rx squared plus Ry squared, because these are the legs of this Pythagorean triangle. When I type that into my calculator, I get 19.5. Now, what about the angle? The angle theta, theta is going to be equal to, now, just like before, I'm going to be using opposite over adjacent, so it's going to be inverse tan. And I'm going to write a note here. Note, okay, use absolute values. What do I mean by that? I mean, when you plug it in, think of this triangle. Notice when I said I don't have to say minus 4.9 because it was going downwards. That's what I mean by absolute values. Don't put in negative values when I do the inverse tan. So the way I'm going to write it here, I'm going to say the inverse tan of the absolute value of Ry over Rx. So in this case, it will be the inverse tan of 4.9 over 18.9. And then inverse, there we go, inverse tan of that. So the answer I get for that one is 345. Oh, actually, sorry, when I do the inverse tan, I have to look at my little cheat sheet over here. Was 14.5 degrees. Okay, so now the next step is to say, alright, so if this is 14.5 degrees, what is that in counterclockwise from east? So if I go all the way around like this, in this case my direction in counterclockwise from east will be 360 minus 14.5. Right, so that would give me my 345.5 degrees. So my final answer here will be 19.5 meters at 345.5 degrees. So what are my important steps here? My important steps are, for each of the vectors I'm adding together, calculate the x and the y component. Add up all the x's, that's Rx. Add up all the y components, that's Ry. The resultant will be, using Pythagoras, the square root of Rx squared plus Ry squared. The angle will be So first of all, you're going to figure out the angle inside this triangle using positive values, and then you're going to look at which quadrant it's in and figure out what that angle is in terms of counterclockwise from east. Okay, I'm going to do one more example, and then there's your turn, I believe. Okay, so for this next one, I'm going to call this one vector A, that one vector B, and that one vector C. So I'm going to add together AX. Oh, I'll do all the X directions. So looking at that first one, AX will be, you know what, I need to change the north of east, north of west, and north of east. I need to make sure I put that in terms of counterclockwise from east. So let me just erase this for a second. Sorry about this. And let's think about what each of these look like. Okay, 45 degrees north of east. If it's in quadrant 1, in terms of counterclockwise from east, it is still 45 degrees. So that's no problem. For the second one, it is 45 degrees north of west. Now 45 degrees north of west, that's what's 45 degrees. My counterclockwise from east is going to be equal to 180 minus 45. So I'll get 135 degrees. Okay, so for the second one, do a little erasing. For my second one, my angle will actually be 135 degrees. My last one again is north of east. So like I said before, when we do north of east, it's in the first quadrant, so it's still 60 degrees. Okay, now so let's add together all the X components. Let's get some blue involved here. That's all the blue involved. Let's do all our X components. So it's going to be, looking at the first one, 3 multiplied by the cos of 45 degrees, plus for our second one, 5 multiplied by the cos of 135 degrees, and for the third one it'll be 2 multiplied by the cos of 60 degrees. So when I add those all together using my calculator, the sum of all, here I can call this one AX, this one is BX, this one is CX, and my resultant RX is going to be equal to negative 0.414. And looking at my Y component here, AY, BY, and CY, AY is going to be equal to 3 times the sine of 45 degrees. BY is going to be equal to 5 times the sine of 135 degrees, and CY will be 2 times the sine of 60 degrees. And so my Y component of the resultant will be 7.39. Okay, so now we're almost done. Now we're going to say the resultant. It's going to be the square root of Rx squared plus Ry squared, which is equal to 7.4. And my direction is going to be the inverse tan of the absolute value of Ry over Rx. One's negative and one's negative, one's positive, so I've got to make sure that I enter it as a positive. So that would be the inverse tan of 7.39 divided by 0.414. And that direction is 7.4 degrees. So thinking now about which quadrant that is in, my x is negative, so my Rx is negative. Try it again. My Rx is negative, and my Ry is positive. So here's my resultant. So this is the angle that we just figured out, was that 7.4 degrees. So thinking about what that would look like, it would be 180 minus 7.4 degrees. So my direction here is going to be equal to 180 minus 7.4 degrees. Did I get that right? 7.39 over 0. It's 17. Oh, got the wrong one. I think I recopied down this 7.4 over here. This one is actually 17.8. Okay, so fixing this over here, 17.8. So my direction will be 162 degrees. So my answer here at the end will be 7.4, and my units were meters per second at 162 degrees. Okay. I think I'm going to pause that now for the video, and I'll come back again for that last one.